It looks like you're going to be outnumbered.
That's okay.
There's a big Zoom group here. So we've got one person in person and everybody else in Zoom. So if you're out there in Zoom, I can't see you quite as easily, of course. So just holler up if you have any questions for me as we get into the review here. I know there's a chat box on this Zoom thing, but I may not have it up in front of my face the whole time. So just unmute yourself out there if you've got questions in Zoom and let me know. I will try my best to help out. Okay. Let's see. What do I need to mention? Don't forget about the homework that's due tonight. About half the class has already turned it in, and I've already graded them. So that's good. I'm ahead of schedule on that. And if you have questions about that assignment, I do have office hours tonight as well, starting at 7. So you're welcome to come to that. And pretty much every day between now and next Tuesday when we take our final, I'm going to be mostly around quite a bit of the time. So you can always stop by and hang out in the study room outside my office. If I've disappeared, I probably won't be gone for long. So anyway, that's that. The other thing is, I know a lot of people are working on learning their proofs from the proof handout that is in the final exam resources folder. Just want to re-encourage you again to consider trying to just do those early. Part of the reason for that is that I can pretty much just give you the time. Like there won't be any like time limit on that. I mean, you know about how long you're going to need probably, but there won't be a real time limit on that. So you'll be able to just come in and whip them out. And then on Tuesday, you won't have to do that. You'll just focus on the rest of the exam. So I'd recommend working on those ahead of schedule as well. And you can come into any office hour and do those at that time. As for the rest of the exam, which will be 75% of it or so, 70 or 75% of it, I have not written it yet, but you know that it will be a mix of definitions, so stating definitions, stating theorems, maybe giving examples of things. I might give you an item that's a true or a false item, but I would probably tell you this is true, give me a proof, or this is false, give me a counterexample. Those kinds of things. You could expect fairly even coverage of all of the material from the entire semester. So please don't neglect the stuff that we learned for the first 2 midterms. So this takes us way back to talking about sets and functions and just basic things like domain and range and whether they are finite or countable or uncountable. Some of those things are maybe a little bit back in our minds now because it's been a few weeks. So the thing to do, I think the thing to do for that would be to go back to the midterm resources folders and maybe review the midterms. So review midterm 1 and 2 especially. I think this most recent midterm is still probably fairly fresh, but certainly the older midterms might not be quite as fresh, and I would recommend going back to those because I am going to ask you questions about sequences. I am going to ask questions about countable and uncountable sets. It's not just going to be about derivatives and integrals, even though that's the stuff obviously that we've done more recently. So what I'm planning to do today, and then also again on Monday when I do a second session, is just a bunch of practice problems, just like we did the previous review sessions. And I'm going to kind of mix it up, try to jump around and cover a lot of different things and kind of poke you about certain topics that might, the idea here is not that you're going to just come to these review sessions and then like be ready for the exam, but hopefully you will get reminded about topics that maybe you're already comfortable with and don't need to spend much time on, but maybe also be reminded about something that has kind of slipped off your radar that you need to kind of go back to one more time and review again. So Anyway, that's just my thought about what I'm hoping that you guys will get out of this review session. Does anybody have any general questions before I actually do jump into my little list of problems here? Let's just see here. Okay, oh, I've got 6 people in Zoom now. Wow. Okay. All you guys wanted to stay in the air conditioning today. It's definitely hot outside, so. Okay, well, if not, I'm gonna jump in and I just wanna, so this will be my review number 1. I'll try to just number the problems and pick up on Monday with problems that pick up from here. Let me know if you're having any trouble reading anything on the board here, guys. But I'm gonna start off with that result that I mentioned in class that I was gonna do during the review session this weekend. I'd like to just do it so I clear my conscience about that one, which is the following problem. So I'm going to assume that I have a function f, which is an element of the Riemann integrable functions from a to b. And what I want to do here then, guys, is I would like to prove 2 things. First of all, I would like to prove that the absolute value of f is Riemann integrable from a to b. And then secondly, once the absolute value of f is Riemann integrable, then we can talk about the value of the integral. And there's a relationship between the integral of f and the integral of the absolute value of f. Namely, the integral from a to b of f, absolute value of that is less than or equal to the integral from a to b of the absolute value of f. Okay, so I stated this in class recently, but then we didn't actually prove it. This was corollary 6.1. I think it's part 2 of that corollary. So it is in the book, and we did write it down and talk about it a little bit, but we didn't actually prove this one. So I'd like to start off by working this out as kind of a warm-up, I guess you could say, get things rolling today. So let's try to prove that if f is Riemann integrable, then the absolute value of f is also Riemann integrable. Any suggestions about how to approach proving that a function is Riemann integrable? I don't know if you guys all caught that, but we only have one person here in person. And the suggestion was to use theorem 6.2, and that makes good sense to me. So we're going to use theorem 6.2 for the first part of this. So apply theorem 6.2, and I won't write it all down on the board again. This is one of the proofs that's in the theorem list, so you could choose to focus on the proof of this one as part of your studying if you wanted to. The way it works is we're going to let epsilon greater than 0 be given. And our job is to come up with a partition such that the upper minus the lower sum of the absolute value of f is less than epsilon. That's what theorem 6.2 really says. But what can I already do once I've brought epsilon into this proof, and we are assuming that f is Riemann integrable? What can I already come up with? Go ahead.
A partition that is u and L or less than.
Yeah, there's already going to be a partition for f, right? But ultimately, we have to come up with a partition for the absolute value of f. It's like, where is it going to come from? This is always my thought. Like, how am I going to create this partition? Well, the fact of the matter is, we already obtain a partition from f being Riemann integrable. So what we can say is, thus, there exists a partition, I'm going to call it P, that is in the script P of AB. That's the set of the partitions of AB, such that U of PF minus L of PF is less than epsilon. And I'll point out here again that we don't have to put epsilon here. We can put anything here that we want, because remember, we're assuming that f is Riemann integrable, which means that no matter what I put here, right, I can find a partition such that UPF minus LPF is less than epsilon. So guys, this is already partial credit, right? If you see a test question, you're being asked to prove that something's Riemann integrable. If you know to use this theorem, even if you don't remember the theorem number, right? I would like to apply this theorem and just say let epsilon greater than 0 be given, and here's the partition P. That's definitely the first part of it. Now, ultimately, what we want to look at is U of P of absolute F minus L of P absolute F. Would there be any reason to think that we would need to use, or that we should use, or that we even can use a different partition?
Yeah, I'd say we have to use a different partition.
You think we have to use a different partition? So here's my interval from A to B, and I've got my function, kind of bouncing around somehow. So that's my F right there. Just kind of, I always like to have a visual of the situation. And what we know is that we have obtained some partition here. I'm just going to draw some tick marks, something like that. That's a partition of the interval AB that works for F, such that UPF minus LPF is less than epsilon. So if we were going to modify our partition somehow, my first question would be, how would I even do that? Like, would there be any logical? Keep in mind, we really don't know what the function is. I'm just kind of drawing an example here. So it's kind of hard to think about see, if I had say a partition of AB, and then I was trying to prove that the function was Riemann integrable on BC or from AC, then I could imagine taking this partition and creating another one here and then modifying the overall partition. Or even if it was the same interval, if I had two different functions, maybe there was also a G here, right? And maybe you had, a different partition for G, right? I could imagine sort of taking a common refinement of the two partitions. But in this case, I only have the one function. I only have the function F, right? And so I have that original partition P. The only thing I'm going to do is take the absolute value of F, which will just basically make everything positive. Anytime it goes negative, it just stays positive, something like that. But I'm not doing any other major modifications. Hey, guys. All right, the in-class crowd is starting to catch up to the Zoom crowd now. So I actually am tempted to believe that more than likely I'm going to actually stick with the same partition here. Keep in mind that when I write UPF minus LPF less than epsilon, that's really saying that the summation I going from 1 to n of big Mi minus little mi, right, times delta xi is less than epsilon. So that's really what this is saying. And my question is, if we take, let's actually add a little notation here. You've seen me do this a few times. I'm going to put F here to emphasize that these are the big M's and the little m's for F. My question is, and we just need one little note here, guys. We just need one little note. Does anybody have a thought about how the big M's and little m's for the absolute value of F would compare with the big M's and the little m's for F itself? So if I take the absolute value of the function, I no longer allow the function to go below the x-axis. I move everything sort of positive. Would it be possible for the difference between the supremum and infimum values to get bigger?
Yeah, I would assume it to get bigger. So
you think it could get bigger if we take the absolute value?
Yeah, if we take the absolute value of the function, the difference should be bigger.
Let me just check. So let's take a little subinterval here. Let's imagine that my function does this. So there's my F right there. Okay. If I look at this function, my big Mi is right here, and my little mi is right here. the maximum value and the minimum value. So you can see how far apart they are vertically, right? But what happens if I replace f with the absolute value of f? So the absolute value of f is going to look like that, which is what I'm drawing in blue. Would you agree that now the little mi for absolute f is at 0, but the big Mi is still, well, I guess it's about a tie. But the difference is smaller now than it was before. This is a bigger difference here, right? The big Mi minus little mi, these are for f. This is the difference for absolute f. So Danny, I don't think so. I think if you take the absolute value of the function, the difference between the supremum and infimum values only gets smaller. Yeah, they get closer together, as it turns out. And so, because of that, I claim that if we do u of p absolute f minus L of p absolute f, right, that this is the summation, I going from 1 to n, of big Mi for absolute f minus little mi for absolute f times delta xi. And now since I'm keeping the partition the same, the delta xi's don't change, but the big mi's and little mi's get closer together. So I'm going to replace that here, like so. The delta xi's are the same. And this is already assumed to be less than epsilon right here. So that should do it. That should do it. What do you guys think? Does this seem reasonable? Yeah? Okay, so that's the first part, applying theorem 6.2. Okay, let's look at the second part. Again, interrupt me with questions, guys, if you've got any as we go along. Let's look at part B. Part B is asking us to prove that the absolute value of the integral of f is less than or equal to the integral of the absolute value of f. Now, one thing I can do, this is a good thing to keep in mind, anytime you're trying to prove that the absolute value of one thing is less than another, remember that that can be unwrapped. This goes way back to very early in the semester. That can be unwrapped without using absolute value bars. I can remove those bars by just creating sort of a double inequality between negative a and a in this case. So the way that would look up here is this thing I'm trying to prove is equivalent to what? Negative of the integral from a to b of absolute f less than or equal to the integral from a to b of f less than or equal to positive the integral of from a to b of absolute f. So I can take, this is like my a, I can take this thing here and go from negative a to a, would be going from negative the integral of absolute f to the integral of absolute f, and the thing on the left side gets sandwiched in the middle. That look okay to everybody?
Mhm.
So in other words, this is really what we need to prove. Because it's equivalent to what we're actually being asked to prove. So we might as well prove this, and this one is a little easier to prove. Does anybody have any thoughts about it?
Since we know that is we want to interval. It's gonna be between the upper and lower sums.
Okay, we could get our hands all on those upper and lower sums again, but let's see if we can do this without that. Can we just do this like super surface level without having to, does anybody remember any other results in chapter 6 that was about comparing integrals? So integral of f compared with the integral of g. Did we have any result on this? Cause I think that might give us a faster path. Let me see if I can find what I'm thinking of. Where is this thing? Oh yeah, I found it. Yeah, proposition 6.4 says that if one function is less than or equal to another function, then the integral of the smaller one is less than or equal to the integral of the bigger one. Well, guys, this is actually just clearly true that the negative of absolute f of x is less than or equal to f is less than or equal to absolute f. Right, so if you take your function, it will always be less than or equal to its absolute value. And it will also be greater than or equal to the negative of its absolute value, right? So this is true, you know, for all x in the closed interval AB. So then by proposition 6.4, which we did in class 2 or 3 lectures ago, the integral from a to b of negative, I'm gonna pull the minus sign out because that's another property that constants can be factored out. So negative of the integral of absolute f is less than or equal to the integral of f is less than or equal to the integral of absolute f. Which is exactly what we needed to show. So actually, there's not a lot to that part of the proof. We can just immediately get to the conclusion just like that. How does that look? Does that seem okay to everyone? So we have now filled in this gap that I didn't prove during the class, proof by postponement, that I actually came back and finished it. So we got the 2 parts down here. Okay, so theorem 6.2, it's a big deal. We used it a lot to prove Riemann integrability, but of course to evaluate integrals, this theorem isn't so helpful. If we actually want to evaluate these integrals, then we have to use something like the fundamental theorem of calculus, which is what we just learned this week. So I'm gonna go ahead and erase it unless there's any comments or questions from the peanut gallery out here. So far, so good? All right, let's go on. I have a lot of questions, so I might as well jump through them. I don't want to just like stand up here and solve problems though without even thinking about these things. Like I could go much faster, but that isn't the way normally we're going to solve problems. So we should do this a little bit more systematically. Okay, I'm gonna jump around. I'm gonna jump around on the topics a little bit. So here comes number 2. Let's show that the sequence xn, which is going to be 2 plus 2 to the 1/2 plus 2 to the 1/3 plus ... plus 2 to the 1 over n, all over n, converges. Ooh. Interesting. First time I saw this, I was like, I have no idea. But actually, it's kind of a nice one. So we have a sequence. We're asked to prove that it converges. Of course, we have the definition. Let's not forget that. The definition of xn converging to x. Let me just maybe write it down again. This goes way back to chapter 3. What this means is xn converges to x if and only if for all epsilon greater than 0, there exists an n naught in the natural numbers such that if n is greater than or equal to n naught, then absolute xn minus x is less than epsilon. So that's a definition that we could use. Does it seem very promising here?
to do, find a subsequence and show that that converges?
Does having a convergent subsequence mean this, the sequence converges? Here's a sequence. It's got a subsequence of consisting of the odd ones. And the odd ones definitely converge, but this sequence never converges. So finding a subsequence that converges wouldn't work. If we were disproving convergence, then we could find a subsequence that doesn't converge, and that would imply that the original sequence doesn't converge. Because remember, we have a theorem. Let's just remember this theorem. The theorem says that if a sequence converges, then every subsequence converges to that same limit. So if you had a subsequence that didn't converge, that would prove that your sequence didn't converge to begin with. But here, of course, we're proving convergence, not divergence. Does this definition seem promising? There's one very challenging thing about it. And that is that in order to use this definition, you have to know what x is, right? And notice that the question didn't even ask you for that. That's kind of a tip that maybe that's a hard thing to figure out, right? It's the question is not asking us what is the limit of the sequence. The question is just asking us to show that it converges. Does anybody remember any tools that we ever had that we were like proving that something converges without actually knowing what it converges to?
Didn't want to.
Okay, the monotone convergence theorem, that was actually one of the theorems on your list from a while ago. I don't think it's on this list, but anyway, but it's a very well-known result. And so the monotone convergence theorem says that if you have a sequence that is bounded and monotone, then it converges. So I wonder if so instead of the definition, let's think about that. So for the solution, let's see if we can apply, I always refer to this as the MCT. Again, you don't need to know the numbering of it. MCT, which just says again that every bounded monotone sequence converges. Every bounded monotone sequence converges. So let's look at this. Do we think that it's bounded? Do we think that it's monotone?
Gonna hope so.
We're gonna hope so, yeah. Actually, I know I have a fair number of people that are in this class that are doing some kind of stats or actuarial or whatever. So you might recognize that what we have up here is like an average. You have n things added together on top and dividing by n. So you're taking the average of the terms in the numerator. Now, as you take nth roots of 2, if you take 2 and then the square root of 2 and then the cubed root of 2 and so on, those numbers are getting smaller and smaller and smaller, which means that when I think about the whole average, it should be going down. So my suspicion is that this might be monotone decreasing, right? So let's see if we can try to write that as a claim here. Xn is monotone decrease. By the way, I like to do the monotone issue first, because if I can prove that it's monotone, whatever, that gives me half of the bounded part. Because for the sequence to be bounded, it has to be bounded above and bounded below. But if it's a decreasing sequence, then it will be bounded above by the first term of that sequence, right? So that's one way to think about it. Yeah, so I'm hoping that we can prove that this thing is monotone decreasing. So the way that's often done is by induction. So you could look at, so we could look at x1. X1 is equal to 2, right? And x2 would be equal to 2 plus the square root of 2 all over 2. Which if we want, we can write that as 1 plus, radical 2 over 2. And so it's clear from this that x2 is less than x1. Square root of 2 over 2 is obviously less than 1, so the base case, as I like to call it, seems to hold. So we'll call this the base case. Well, actually, so when I'm saying monotone decreasing, what I mean is, xn is less than or equal to xn minus 1 for all n. I guess in this case, the way I've set it up, it would be greater than or equal to 2. Right, so x2 is less than or equal to x1. We could call this the base case of n equals 2. I don't really have an n equals 1 case for this because there is no x0 defined. Okay, so far so good. So now we have to kind of do this induction thing. We have to for the induction step, we have to assume that it's already true for n, and then try to prove it for n plus 1. Or actually, I might assume the n minus 1 version, if you don't mind, just so I can be consistent with my notes. So in other words, I'm going to assume no, actually, sorry, I keep changing my mind. Let's just assume this as stated. Let's just assume this as stated. So assume that xn is less than or equal to xn minus 1. Let's just do that. That is kind of an n minus 1 version. So what does that mean? That means that 2 plus 2 to the half plus 2 to the third plus dot 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 plus 2 to the 1 over n all over n would be less than or equal to 2 plus 2 to the half plus 2 to the third plus dot 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 plus 2 to the 1 over n minus 1 all over n minus 1. And I'm going to try to prove that the same thing is true for the next version. So we need to show that 2 plus 2 to the half plus 2 to the third plus dot 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 plus 2 to the 1 over n plus 1 all over n plus 1 is less than or equal to 2 plus 2 to the half plus 2 to the third plus dot 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 plus 2 to the 1 over n all over n. Okay. And by the way, guys, what we have to do over here is kind of a technical manipulation with the inequalities. You have to think about the big picture of this exam, right? If you get stuck fumbling around with these inequalities, that is not a good reason to erase everything you did, because I can give you partial credit for knowing the MCT, for recognizing that it's going to be monotone decreasing, even for doing the base case. I like to give partial credit for every little part of the solution that has been shown. So you guys probably already know this by now, right? So definitely, this is a little intimidating, but it's also, you know that this isn't going to be done with some big theorem. This isn't going to be some really deep concept that's like some huge 350 thing. This is going to be just algebra. It's literally going to be algebra. And so I wouldn't get hung up on something like this. I guess that's what I'm trying to say. I would try not to get too hung up on this. I might suggest that we kind of work backwards a little bit on what we need to, instead of trying to force this into the proof of this, I'm just going to take what I'm trying to prove and make it look nicer. And of course, one way to do that is to cross multiply everything. So I'm going to just remove these fractions, guys. So this is going to be an n with a 2 plus 2 to the half plus dot 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 plus 2 to the 1 over n plus 1 less than or equal to, and then on the other side I have an n plus 1 with a quantity of 2 plus 2 to the half plus dot 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 plus 2 to the 1 over n. So something like that. And I can see that if I was to multiply everything out on both sides of this inequality, some things would cancel. Like here I see a 2n, and here I see a 2n. Right? And actually, here I have an n times a square root of 2. And here I have an n times square root of 2. You see that a lot of the terms are actually going to cancel. And in fact, all of these terms on the left, every single one of them can be canceled with something on the right, except this last one. Because this last one has the exponent involving n plus 1. So let's cancel as much as we can. Let's cancel as much as we can, which would be everything on the left except for the last term. Now on the right side, we have already canceled everything that's multiplied by n. So the only thing left is this 2 plus 2 to the half plus dot 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 plus 2 to the 1 over n. Okay. Okay, so maybe we're gonna get somewhere with that. So actually, just to be totally clear, I have n multiples of 1 over 2 to the 1 over, sorry, n multiples of 2 to the 1 over n plus 1. I'm gonna rewrite that if you don't mind as 2 to the 1 over n plus 1 plus 2 to the 1 over n plus 1 plus 2 to the 1 over n plus 1 n times. N times. So I have n of those on the left. And I'm going to leave the right exactly the same. Oh my gosh. There are n terms on the left side. There are n terms on the right side. And this is equivalent to what we need to show. We're trying to prove this, which is equivalent to this, which is equivalent to this, which is equivalent to this, and I want you guys to look at this. Is this true? I have n terms here, and I have n terms here. What's the difference? Well, on the left side, I'm taking larger roots of 2. Like the n plus first root of 2 each of those times. Actually, if you go term by term, this is bigger than that. This is bigger than that. This is bigger than that, and so on and so on and so on. But even this one, which is the smallest term on the right side, it's still bigger than this guy. So guys, this is clearly true. And actually, this is true for all n. For all n in the natural numbers. There's no differentiation based on n here. So you know what we've just discovered? We've just discovered that we didn't really need to do this by induction. This fact was already going to be true anyway. This is xn plus 1, this is xn, and xn plus 1 is less than or equal to xn, and we've made it equivalent to a bunch of things that led us down to something that is clearly always true. So we actually don't need to use induction this time. Now we've seen examples where we do, right? Generally, the cases where you do use induction are when xn is defined in terms of xn minus 1. See here, this is an explicit formula for xn. And so in some sense, you would think, oh, well, I could just try to prove directly that it's monotone decreasing. And that's essentially what this is right here. Okay, but I don't want you to forget that there are applications of the MCT for which you really do want to use induction. And that's often because the sequence is defined recursively, right? We're defining xn in terms of xn minus 1 and xn minus 2 or whatever, okay? But anyway, this first claim now should be good to go. It is a monotone decreasing sequence. And now our next claim, are there any questions though? So far, so good? Great. The next claim is that xn is bounded. Well, let's see, it needs to be bounded both above and below. Anybody wanna help me with either one of those?
Since it's monotone decreasing, it's bounded above by 2.
Exactly, so since xn is monotone decreasing, it is bounded above by x1, which was equal to 2, the very first term of the sequence, right? Okay, so it's bounded above, that's half the battle. That's why I like to do the monotone first, because then I get very quickly can get that part done. It also needs to be bounded below. Does anybody have a lower bound on this thing?
We can go for 0.
Yeah, I would just go for 0. Remember, you don't have to go for the best, you don't have to find the best answer. So we could just go for 0. All of these terms are positive, right? So let's just say, since xn is always greater than or equal to 0, that would be for all natural numbers, right? Then xn is bounded below by 0. Absolutely true. Okay, so it's bounded above and it's bounded below. So it's bounded, it's monotone, and so thus xn converges by the monotone convergence theorem. That would do it. That would do it. Okay. But again, if you got fumbled up in this algebra over here, right? That doesn't mean this has to be a 0 problem for you, right? There's a lot of other things you can address over here, the big picture of the solution, and as much of it as you can write down, you should, because I can give you credit for knowing those things. Okay, super. So that's a nice topic. We certainly have seen several examples of the monotone convergence theorem. We've also seen examples of proving convergence of sequences just from the definition. So that epsilon n naught definition that I wrote down a few minutes ago should also be reviewed if necessary, because I mean it's been a while. You know, that's also, I think, obviously a valid technique. Okay, but for the time being, I'm going to move on. Let's go to number 3 here. And what I want to do here is, I'm going to suppose that the limit as x approaches a of f of x is equal to infinity. And I'm going to suppose that the limit as x approaches minus infinity of g of x is equal to a. It's kind of interesting. And then I have one more thing I need to assume here. So I'm also going to suppose one more thing, guys. I'm going to suppose that there exists a positive number m with g of x not equal to a for all x less than negative m. So this just means that if you plug values of x in that are way negative, it's never going to equal a. Okay, so keep that in mind. Then here is what we're going to prove. We're going to prove that the limit as x approaches minus infinity of f of g of x. Okay, I don't think I've done this with you before. So we're actually going to compose the f and the g together. We're going to try to show that this limit is equal to infinity. All right, well, this is going to be a lot of, well, there's a lot of definitions to review. Like, what does it mean for the limit of f of x to equal infinity? What happens if you take the limit as x goes to minus infinity of g of x? And so on. And here we have infinities in 2 places. in this thing that we're trying to prove. Strict time out here. You wanna get in there? I'll just look at it a little bit, thank you. Okay, so. This is a composition of functions. Let's just see, does it even make sense? So as x gets big negative, we first put it into g. What's g of a really big negative number? Well, it's approaching a. So then the g of x part is like approaching a, and then what happens to f when you plug a number that's close to a into f? Oh, it becomes close to infinity. So it does seem like a reasonable, the statement is reasonable. The statement is reasonable, but now this is gonna force us to really understand the definitions. Right? So let's start with what we're trying to prove and just get the definition down. I mean, basically, if you want to prove that the limit of a function is equal to infinity, you have to start with some arbitrary, what I used to call alpha, greater than 0, and then your job is to come up, I guess in this case, with a beta that is negative, such that if x is less than beta, then f of g of x is greater than alpha. Can I write that down? Maybe I should, okay? And let's just get the statement written down here. If I put this on the exam, I probably would have a part A and have a part B. What's the definition of that? What's the definition of that? And then, you know, get some of these things down here. Okay. Hi. So we need to show, so for all alpha greater than 0, there exists a beta less than 0, such that if x is less than beta, then f of g of x is greater than alpha. That's actually what we need to do. Okay. All right, so if we were actually doing our proof here, so maybe I'll actually start writing the proof here. As you can imagine, in a minute, we're gonna go over to some scratch paper. We always do these by starting the scratch paper. The proof would start off with let alpha greater than 0 be given. Right? And what we're really looking for is we want to get this f. We want to get f of g of x to be greater than alpha. That's really the goal here. And so we really need to get g of x to be close enough to a in order for that to happen. See, what does this say? This says we're assuming that the limit of f of x is already equal to plus infinity. That actually means that if I use this assumption, that there already exists a delta. It's not beta yet, because x is not going to minus infinity right here. X is going towards a. So from this first assumption, guys, there exists a delta. Let's just run with that, okay? So then there exists a delta greater than 0 such that, see, I don't see the whole proof yet. I really don't. I'm just taking it baby steps, one step at a time. So such that what? If 0 is less than absolute x minus a is less than delta, then f of x is greater than alpha. So I can already find this delta such that if the distance between x and a is less than delta, then f of x will be greater than alpha. Now, it's not really f of x that we want, though. We really want f of g of x to be greater than alpha. So you know, we actually can edit this because there's nothing that says that you have to call this x. You can call this g of x. As long as you call this one also g of x. Sorry, I wrote that really small. Let me try to write that a little nicer so that the people in Zoom can clearly see it. So we can modify our x to be g of x if we want to. The definition basically just says if you have anything that's within delta of A, then f of that thing will be greater than alpha. So I'm allowed to replace the x with the g of x in that statement. So I didn't find my beta yet, but I did find a delta. I found a delta such that as long as g of x is not equal to A, g of x is not equal to A and is less than, g of x minus A is less than delta, then we'll get what we want. Okay. But I still have to come up with a beta. And we've kind of used this assumption so far already. But we need to make sure that the g of x is getting close to A, right? It needs to be within delta of A, otherwise this doesn't apply. So that's where we're going to need to use this one now. Okay, so from that assumption, there is going to exist a beta. Okay, so let's try and bring that into the equation now, into the solution. So we also have that there does exist a beta less than 0 such that if x is less than beta, then absolute value of g of x minus A is less than whatever we want. Remember, we're assuming this, right? We're assuming already that this limit exists, so this would say, like, what is this definition? This definition would be for all epsilon greater than 0, there exists a beta less than 0 such that if x is less than beta, the absolute value of g of x minus A is less than epsilon. So I get to put whatever epsilon I want right here. What do you suppose I want to put right here? The delta that's already showing up in this proof, right? It would make sense. That would totally make sense that would be it. That would totally make sense. Okay. Except that there is still a slight problem. It may look like we have found our beta and we're going to go riding off into the sunset and everything is going to be great. Because what did we need to do? We needed to find a beta less than 0 such that if x is less than beta, then f of g of x was greater than alpha. Well, right now I have a beta less than 0 such that if x is less than beta, then absolute g of x minus A is less than delta. And if absolute g of x minus A is less than delta, then f of g of x will be greater than alpha. It looks like that's what we wanted, right? So what I'm looking for from anybody, either in Zoom or in person, is what is the problem with this proof? Why can't I just say, okay, there's my beta, less than 0. Let's just check if it works, right? To check that beta works, I let x be less than beta. All right, I did that. If x is less than beta, I now need to prove this. But I already know that if x is less than beta, then g of x minus A will be less than delta. And if g of x minus A is less than delta, then domino effect, I get f of g of x greater than alpha. What is the problem?
Haven't used M.
We have not used the M that is in the statement at all, right? So here is really the problem, and it's a subtle point. what this last sentence tells me is that as long as x is less than beta, the absolute value of g of x minus a will be less than delta. But it is actually possible that g of x minus a could be equal to 0. 0 is certainly less than delta, right? If g of x was equal to a, then this statement would not apply. Because this statement says that if g of x minus a is less than delta and greater than 0, then we can get the conclusion that we want. Right? So you know what I'm gonna do? I'm gonna come back here and I'm going to change this beta to a beta 1 because I have realized that that is not the correct beta. It's still valid, but this is not the final beta that we need. We also need our beta to be negative enough such that the only x's that we're ever looking at are the ones that are less than negative m. Because as long as x is less than negative m, we're good with g of x minus a not being equal to 0. Okay, so now does somebody want to tell me what the beta is? We're going towards negative infinity, so we would pick the min. We would pick the min of what values?
One and negative.
The beta 1 that we found a moment ago, because we need that, because we want x to, remember, x is gonna be less than this beta. So x needs to be less than all of these things, right? So beta 1, that's good, because we got x less than beta 1. And negative of m, that's right. Negative of m. Notice, by the way, that both of those will be less than 0. So this beta is a negative number. Okay, that's the final beta, and now I think we're going to get the proof to work. Let's check the proof now with that beta. So let's assume that x is less than beta. If x is less than beta, then x is certainly less than negative m. So absolute of, if x is less than negative m, then 0 is less than absolute g of x minus a. Also, x is less than beta 1. So absolute g of x minus a is less than delta. Putting both of them together, we now conclude hence that 0 is less than absolute g of x minus a is less than delta. We get both sides of that inequality from that. We get both sides of the inequality, and now we have the underlined part. If g of x minus a is between 0 and delta, then f of g of x is greater than alpha. Okay, so we conclude that f of g of x is greater than alpha. Whew. Took a little doing.
How
Lindsay.
do you know that if we're using the min or the max again?
It's basically because we want x to be less than 2 different things. It needs to be less than 2 different things, and so to make sure that it's less than both of them, you take the smaller one. If you need to, draw yourself a number line, and here's 0, and you've got your negative m here, and you've got your beta 1 here, right? So you always can restrict your x's by as much as possible, and that will, just by gut feeling, it means it's more likely your proof will work. So in this case, you want to only be looking at x's that are less than both of these. So it would be less than the smaller of the two. So I'm just drawing an example here to kind of visualize how that would work. Okay. Guys, the truth of the matter is, I probably wouldn't do this to you because there's this is pretty complicated, like there's several kind of new definitions and I'm composing the functions again. It's a great review session question. As for the exam, I'm not sure I would do one that has so much complexity. I might do a limit at infinity. Right, so, but the purpose of me bringing this up now is, again, not that you're gonna walk out of here like thinking, oh, this exact problem will be there. Rather, you remember now you need to review limits at infinity, right? Both approaching, so we have approaching minus infinity and the value of the limit being infinity. And you can do pluses and minuses on either of those. There's a bunch of definitions for that. So that would make a good question. I have a part A where I ask you one of those limit at infinity definitions, and then part B, I ask you to prove something that's really just a one part thing. You know, that would be more likely. So anyway, and you know, I think we've certainly done examples before where we had like F plus G. And that might be something that would be a little bit easier to handle. Anyway. Okay, so just to remind everybody about some of these things, that's kind of what I'm trying to get at here. Let's do another one. Let's do number 4 here, guys. Let's define a function. I'm going to call this little f going from Q to R via f of x equals. And I'm gonna do the arc tangent of x. And what I want to know is the range of f finite, countable, or uncountable? And you can circle all that apply. Just a quick reminder, a finite set is always countable. The definition, I better remember these definitions. A countable set is one that, so A is countable if and only if A is finite or there is a bijection from A to the natural numbers. And you might want to review some examples of countable and uncountable sets. Remember that for example, the integers are countable. So I can write some of these down. So Z is countable. Another good one is Q, which I actually see in this question. It's part of the domain of the function. Q is countable. Also, cross products of countable sets. So A cross B is countable if both A and B are. So if A and B are countable, then so is A cross B. So you can do a finite direct product, also called Cartesian product of two finite countable sets, and it'll still be countable. And in fact, the biggest result was the one that says that any countable union of countable sets is countable. And that one is in the list of theorems as an option for you to study for the final. A countable union of countable sets is always countable. Make sure you state that correctly. A countable union of countable sets is countable. There's 3 countables in that statement. I've seen people write a union of countable sets is countable. I've also seen people write a countable union of sets is countable. Not true. Right, so you have to have it in there in both places. A countable union of countable sets. Sorry, I don't mean to harp, but if it's not written all the way out correctly, then it's like, oh no, that was an easy one that somebody missed. So just to make sure you're very cautious about writing that down. Anyway, so these kind of things are good to know. The main one that's uncountable would be R. But even smaller than that, if you just take any, well, any interval really. You could just take any interval. An interval is always uncountable. And so if you took more than one of them and took the union, that would be uncountable. if you go back to the midterm one review, and even on the exam, I think I had some examples, and I said, is it countable or uncountable, finite, countable or uncountable, and you had to circle the answer. If this is a topic that you're feeling like, oh my gosh, that was so long ago, I don't remember, then go back to your first midterm and just review, there was a whole problem on this. Anyway, this is another problem that I don't know how great it would be for the exam because it involves, you know, the arctangent function maybe is not something that's on the tip of everybody's mind. Let me just remind you how the arctangent works. So here's the tangent of x. Just your usual tangent graph looks like this between negative pi over 2 and pi over 2. So the tangent graph has all these arms, these branches as they're called, that go kind of between asymptotes. You have a bunch of vertical asymptotes. So that's the way that the tangent graph looks. So the arctangent graph is basically just flipping the inputs and the outputs. So now the outputs are going to be going from minus pi over 2 to pi over 2. And the inputs are gonna go like that. So now you have horizontal asymptotes instead of vertical ones. So this would be the graph of the arctangent of x. So again, don't get too hung up on this. Like, I don't want anybody like worrying about the test. I'm like, oh gosh, he's gonna ask me about the arctangent function. Maybe very unlikely. It's more, I just wanted to come up with a decent question that I haven't shown you before. So the question is about the range of this function and whether it would be countable or not. And I'm wondering if anybody has any thoughts about that. If you think about it, the only outputs that you're looking at are the outputs from the rational numbers. So you're not actually taking this entire filled in line here. It'd be more accurate to think of it as just a whole bunch of, here, let me draw all of these. A whole bunch of dots where you're outputting the rationals that are on this, like, here we go, I can go faster. Right, so it's kind of like a speckled sideways tangent branch. So it's not the, because if it was the entire thing, if the range was all outputs from minus pi over 2 to pi over 2, I would say that's uncountable. Because this is just like any old interval a, b. Okay, but the range of this function is not all of that. The range of the function is just the dots that are on that curve. And that's less points than the entire graph. Is it enough less to make it only countable?
So are you saying that it could be, it could be countable infinite or like not?
Yeah, I'm wondering whether this is countably infinite or not. Now, what I was saying is if I include all of the points on that curve, not just the ones I highlighted with dots, if I took the entire curve, I would argue that that's uncountable because then the range would have been the full interval from minus pi over 2 to pi over 2. But if I focus only on the outputs that are coming from rational inputs, then I'm actually, this is kind of a misrepresentation. We know that the rationals are dense here, so I can't really draw it perfectly. But I'm only grabbing the rational valued outputs here. Now you can plug in a rational number and get an irrational number as an output. That can happen. But it's not, the question is not whether the outputs are rational or irrational. The question is how many of them are there?
Since f is a function, it cannot have more than one output, and you're putting a countable number of things into it. Therefore, you get a countable number of things out of it.
Absolutely right. Did everybody catch that? Right? You have a countable domain, right? And what is the feature of this function? Actually, I don't think I think we could phrase this very easily. Is there something about this function that you could say it's a nice property of the function? It's monotone. The function is monotone, and in fact, it's because it's monotone, is it possible for two different inputs to give me the same output? It's actually strictly monotone. If you think about it, in the review session for I think I used this function in the review session for the third midterm. And we proved what the derivative of it was. And the derivative of it was 1/1 plus x squared, which is strictly positive. And so that means that this function is strictly increasing, which means that the function is
Countable.
a set could be countable, a function would not be countable. What is a nice, it's okay, good try. Is there a nice property that a function could have that is related to this topic?
Oh, bijection.
Bijection is close, but I would argue this is not a bijection.
Surgeon. Because everything you're putting in has an output. Oh, wait, no, injective, because you want it to be, you want it to be.
Keep talking, you'll get it right eventually. Yeah, guys, this is 1-to-1. This is
Yeah.
1-to-1, right? F is 1-to-1, it's injective,
Yeah.
right? Since F is strictly increasing. Since F is strictly increasing, if anybody questions you, why is it strictly increasing? You just say, since, I'm using the word since too many times in one sentence. Since the derivative of it is 1/1 plus x squared, which is positive. So if you have a derivative, now not every function is differentiable, but if your function is differentiable, you can use the derivative to argue that the function is strictly monotone increasing. And therefore it is 1-to-1. And guys, if you have a function from a countable domain that is 1-to-1, that's actually one of our early propositions back in the beginning of the semester. So let me come back over here. Since Q is countable, I would want you to write that down. Since Q is countable and F is 1-to-1, then the range of F, which is just all of the outputs of F, is countable. This is by a proposition. I think it's proposition 2.12. Let me quickly flip there and just, I'd like to give you the good reference on this one. Yeah, it's basically proposition 2.12 part 2, except it's in the contrapositive formulation of it. But that's okay, we can deal with that. Oh, no, it's by proposition 2.12 part 1. Yeah, I was in the right part, but I was reading the wrong one. Yeah, so if you want to refresh your memory about that, guys, this function, okay, so let's just remember, the function is 1-to-1. So it actually is a bijection. F actually is a bijection from its domain to whatever its range is. So the function as it's presented is not onto. But if we just kind of change the current codomain to be whatever the range of the function is, you're kind of just cheating and cutting down the codomain to be what the outputs are, well, then it is onto. A function is always onto whatever it's onto. And so in this case, you would have a bijection now. And bijections, of course, preserve countability for sure. So yeah, so this would be so this one would be countable. It's definitely not finite. It's definitely not finite, but it would be countable. Okay.
Dr. Andy,
Yeah.
you said the theorem of accountable union of countable sets is countable is part of the list of theorems?
Yeah, it's theorem 2.4. It's the first one on the list.
I thought 2.4 was Q is dense enough.
No.
I probably done the wrong one.
Uh-oh. Yeah, guys, gotta make sure you have the right theorems from the book. I should have stated them on that handout maybe. But anyway, I didn't do that, so you'll have to just be super careful. Oh, boy. Okay, let's go on to another problem here, guys. Yeah, let's do number 5. This one is a true or false. As I said, I probably won't do true false on the exam, but I might state it and ask you. I'll say it is true, prove it, or it is false. Disprove it with an example. Let's try this. So here's the statement, true or false? If f and g are functions from R to R, and if these are both differentiable at some point, I'm gonna call it A in the real numbers. So if f and g are both differentiable at A, then the question is it true or false that g composed with f must be differentiable at A? Okay, so it's a good question. I will tell you that we did prove, of course, that f plus g would be differentiable at A, f times g would be differentiable at A, f over g would be differentiable at A as long as g is not 0 at A. So I just wanted to bring in the composition again and talk about that, and would that have to be true?
False, because we do not know that G is differentiable at f of A.
Aha, so the point that's going to get plugged into G is not A, it's f of A. So just keeping this in mind, G composed with f of A is G of f of A. So the function f is displacing the point A to some other value f of A, and what if G is not differentiable there? So my gut feeling, along with John's, is that this is probably not true. Because the point A is not stable. The function f is gonna move it somewhere else. So let's kind of, does everybody kind of agree with that intuition? It doesn't seem like it should be true. It's probably gonna have issues. So what we're gonna want to do is think about a counterexample. So we need to come up with two functions that are both differentiable at a certain point, but then somehow when we compose them together, it's no longer differentiable at that same point. Can somebody think of like, it would be like an easy function? And these functions, by the way, they have to be defined on all of R. So we can't have like, f of A turn out to be not an input of G, right? So f and G have to accept every possible input. It's not an issue of the domain. We need functions that are defined everywhere. Is there a function that is nice to work with that maybe isn't differentiable at a point somewhere?
Absolute value of x for g.
Yeah, I'm thinking about absolute value of x, and I think people here are agreeing with that. So the absolute value of x is not differentiable at 0. And if I still don't have my example totally figured out, if I write that down on my test paper, my professor might give me some credit for it, right? So absolute value of x is not differentiable at, let's say A equals 0. Now, this would be a case, you might be wondering, well, I wonder if I have to prove that. If I'm gonna say that on my exam, do I need to prove that? This is, of course, a result we have talked about before. We've even done this example. So if you have seen this in class or in a homework exercise or in a group work, or even on an earlier exam or somewhere in the book, you can cite that. You don't need to prove it. If you're not sure, come ask me. Okay, you can come up to the front of the exam and just come ask me, I'll let you know. If I want, can I just use this without proving it? And I'll tell you. Cause sometimes people they will bite off too much and they'll like basically not do the problem by saying, oh, well, this is something we learned somewhere, and then they're not really doing anything. So I don't want you to have to like struggle and stress about whether you need to prove something or not. So you're always welcome to ask me whether you can take this for granted. So at this moment, I'm gonna take it for granted. Okay, if anybody wants me to prove that, we can. I mean, we can look at the limit definition of absolute value. And we're gonna see that, you know, the derivative function is like +1, +1, +1, +1, and then goes to -1, -1, -1, and there's a sharp corner at 0. So that limit won't exist. That difference quotient limit will not exist at 0 for this function. Right? Okay, so I'll leave that off for now. I'm just gonna save that. So let's try to define these functions. So define f of x to be, somebody wanna give me so I think we've already decided that the g of x is gonna be the absolute value function, right? Remember, that's the one that's on the outside. What do you wanna use for f? Say it again? X plus 1? Yeah, and by the way, we're gonna use a equals 0 here, right? Okay, so we could try that. So then notice that f is differentiable everywhere. And, oh, this isn't gonna be g. I'm so sorry. This is going to be g composed with f. G actually has to be, oh, no. Sorry. Wait a second. I'm fine. I'm fine. This one is. Oh, I know what the problem is. I don't want to use a equals 0. How about we use a equals 2? Something like that. Okay, that's a better idea. So now both f and g, oh, except 2 isn't gonna work with. Oh, that one. Can we, what do we want it to be? -1, yeah. Okay, sorry, I'm just trying to let you guys guide this ship, so. I'm not bailing you out too early on these. Yeah, so f is differentiable at a, g is differentiable at a, so here. Both f and g. Are differentiable, I'm just gonna abbreviate that diffable. At a equals -1. But if we look at g composed with f of x. This is g of x plus 1, which is absolute value of x plus 1. And that function is not differentiable at a equals -1. Looks like a good counterexample to me. Okay. Nice. Everybody feel okay with that? Alright, so that's kind of the right level of difficulty, I think. Not too hard, not too easy. Have to think about it a little bit. It's kind of what I'm always looking for. Okay, let's do another one, guys. We're rolling. Number 6. Any questions out there? Far so good. Let's see what we got going here. Yep, still got a pretty good Zoom crowd. Awesome. Okay, let's go on to another example. Number 6. I'm gonna let A be less than B. And I'm going to define the integral from B to A. So you notice, guys, that when we've done integrals in this class, we've always had to have, our interval was set up in advance. And we always just did, right, the integral from A to B of f. So I never talked about, putting the bigger number on the left side. We don't have an interval here from B to A, because A is less than B. So I have to define this now. Okay, as of this moment, it makes no sense to integrate a function from B to A. So, but of course, what I'm going to do is what you all know, which is that you can switch the limits of integration and put a minus sign on it. So I'm going to define the integral from B to A to be the negative of the integral from A to B. Okay, so then with that in mind, I would like to find g prime of x, the derivative of g, where g of x is the integral from 3x squared plus 5 to 7x to the fourth plus the sine of x of, and then I'm gonna put 3t squared plus 5t plus 1. Okay. So a little build on to what we did this week, I guess. We are, the first thing we want to recognize here, guys, is I am taking the derivative of an integral. Do we have anything about that? Didn't we have the thing with the capital F? If we integrate from a to x of little f, then assuming that little f is continuous, which by the way, this will be, it's a polynomial. Assuming that's the case, then you remember that the derivative of the big F is just the little f. So this is actually the stuff from the homework that you're working on for today. The derivative of the integral of f is just f. Okay. So I feel like I would want to use this because we're taking the derivative of something that's an integral. Can I use it immediately? There's definitely some problems here with using this immediately. The a right here is a constant number. It's a fixed value, and I don't have any fixed values here. So could I do something that would allow me to at least have a better shot at using my theorem 6.12?
Who do you use?
I need to have a constant limit of integration. Sorry?
Kind of shot in the dark. I assume MTV for integrals.
It's possible that could be useful, but I'm more inclined to use this result, which is the part 2 of the fundamental theorem of calculus for integrals. What I'm really getting at is like, how can I deal with the technicality of like the way this is set up, the way these limits are? Can I, which is not really like, I'm not really asking for like a big theorem to use to solve the whole problem. I'm just trying to figure out like, how can I simplify this? Could shift it a little bit. It's not that far off of what maybe you're thinking of the same thing I am actually. What's that?
Something to X. No.
Now that we can't do, because if you just give me a specific value of like, if you figure out g of 5, for example, I can't take the derivative of g if all I know are these discrete values of g, right? How can I make a constant limit of integration? So as of right now, guys, the interval that I'm integrating is from whatever 3x squared plus 5 is to 7x to the fourth plus sine of x. What can I do? We've used this idea a lot. I don't like that interval the way it is now. But if you have a big interval like this, what can you do with it?
You can find an interval inside of it.
You can chop it up, right, into a smaller interval. Why don't I just chop this up at, I don't know, 17? Right, so we have we have the ability to do this, guys. I can just say, I'm gonna put a 17 there. And then I'm gonna add that to the integral from 17 to 7x to the fourth plus sine of x of the same thing. By the way, the 17 is totally arbitrary. You pick any number you want and do that with it. Now, we no longer have to be worried, because we might be worried, right? You might be worried, well, what if the 17 is smaller than the 3x squared plus 5? We don't know that, because we don't know what x value we're talking about. Same thing here. I don't know that the lower limit is less than the upper limit. This is why, at the start of the problem, I wanted to make sure it was clear that it's okay if the lower limit is smaller than the upper, sorry, if the lower limit is bigger than the upper limit, because that's addressed by just doing a sign change and switching the order of the integration. Right, and in particular, if I want to use this theorem 6.12, right? If I want to use this theorem, the constant limit needs to be the one that's on the bottom. So I actually need to edit this first one so that it. So I'm gonna do another step here, guys. I'm gonna switch the order of this integration. So we've just learned how to do that. Just right now, we can define the integral from b to a of f by switching the order. That costs us a minus sign. So now I'm gonna put the 17 underneath and the 3x squared plus 5 on top. 3t squared plus 5t plus 1, and then we'll have another integral going from 17 to 7x to the fourth plus sine of x of the same function, 3x squared plus 5t plus 1. So again, I'm just simply trying to get this to look like something that we can now apply this function to. Okay? Now, this thing here though, guys, we have another problem. This upper limit is not x, and neither is this one. So if I'm looking at the setup of the theorem, it's supposed to be an integral from a to x, and then we take the derivative of it. Alright, so it's a little bit of another problem that we have right now. But what we could say, I think, is we could say that this is negative of capital F of 3x squared plus 5. And then plus f of 7x to the fourth plus sine of x. Agreed? Guys, all of this is g of x. We started off with g of x. G of x is equal to this, is equal to this, is equal to this, is equal to this. So it's negative of capital F. All right, if this is capital F of x, then what is capital F of 3x squared plus 5? Everywhere I see an x, I change it to a 3x squared plus 5. Okay, and the little f is just this 3x squared plus 5t plus 1. You with me? Well, so far, I've just been figuring out how to write g of x. Now I want to take the derivative of it, because the question says find g prime of x. So now, let's see if we can actually take the derivative of what we have here. Okay. So let's do this term by term. In fact, there's a plus sign between them. So I've got two of these terms to do. The first one has a minus. Of course, we all know that minus sign is a constant. We can pull it out. But how do I actually take the derivative? So I know how to take the derivative of capital F of x. It's just little f of x. But I'm taking the derivative of capital F of 3x squared plus 5. So what does that sound like we need to do? This is like a little, I don't know, call it h of x, right? This is like f of h of x, right? And I want to take the derivative of it. So this is actually, guys, this is the derivative of a composition. So whether it's clear or not, I don't know, but when you have limits of integration that don't just have x on them, you can do these. You probably, I remember even in my freshman calculus, they had me do a few of these. I don't know if they, it's not a big point of emphasis, but I remember doing these problems where the limits of integration were not, they had whole functions on them. And you had to actually use the chain rule to do it. So that is actually what we need to do. We need to take, the negative of f composed with h prime of x. So I'll come back in a minute and fill in what that is. And then on the second one, let's call this second function k of x. So I also have to do f composed with k prime of x. So these are the derivatives I have to calculate. Okay, so the first one I have minus, and then you guys all remember how the chain rule goes, right? So this step, now I'm ready to do the chain rule. Gonna use the chain rule here. This is negative of capital F prime of h of x times h prime of x. And then plus capital F prime of k of x times k prime of x. So it would have both parts like that. Okay. And this is where, sorry, and just to be clear, this is where capital F of x, what is capital F of x? Capital F of x is the integral from 17 to x of 3t squared plus 5t plus 1. That's the capital F of x. We're trying to figure out f of the derivative of f of 3x squared plus 5 and f of 7x to the 4th plus sine of x. So what is the derivative of this? Just the derivative of f of x. What's the derivative of just f of x? Exactly, the derivative of just your, by the way, the a value doesn't even matter, it's 17 for what I picked here. But I'm taking the derivative of the integral from 17 to x, so it's just the little f evaluated at x. So the derivative of this one is just 3x squared plus 5x plus 1. Okay, so now I'm just gonna substitute that in, and hopefully we'll get to an answer here. Okay, so thus, what is g prime of x? Hope I have enough room. It's minus of f prime of h of x. So I have to take this thing here, and everywhere I see an x, I have to put 3x squared plus 5. Oh my gosh. So it's negative of 3 times the quantity 3x squared plus 5 squared plus 5 times the quantity 3x squared plus 5 plus 1. That's this part only. I still have to multiply by the derivative of h. The derivative of h is 6x, right? The derivative of 3x squared plus 5 is 6x. So I have that, and then I'm gonna have to do this on 2 lines. I have a big plus sign here, guys. And we'll go down to the next line. On the next line, I'm gonna take f prime of k of x. So let me get some brackets for this as well. F prime of k of x, that's going to be 3 times the quantity 7x to the 4th plus sine of x squared plus 5 times the quantity 7x to the 4th plus sine of x plus 1. And that one gets multiplied by the derivative of k, which is 28x cubed plus the cosine of x. Ooh.
Can you shift the camera to the right just a hair?
Absolutely. Oh yeah, I see. I cut that off there. Sorry about that. Is that readable? This is the
Yes,
plus
for
sign
sure.
right here.
Is there any signs after the 6x?
No. Let me just temporarily move you in here a little closer. That look okay?
Yeah, it was readable where you had it sitting there. We just needed to see that last corner.
Okay. Okay, I'll set it back then. Just wanted to make sure. All right, what do you guys think? This is a combination of the chain rule together with the fundamental theorem of calculus, both hand in hand. It's easy to recognize these problems. If you have limits of integration that involve functions, you're probably thinking about creating names for those functions and using the chain rule to evaluate them. Okay? Good enough? Okay, let's go to another problem then. I'm gonna go ahead and erase this one. Make sure I'm not cutting off the other side of the board now. Okay, I think we should be good. Let's do another one, guys. We've got maybe another 20 minutes here and then we'll call this good for today. Am I up to number 7?
Yes.
Okay, number 7. Okay, here we go. Suppose that f, which is a function from R to R, has a continuous derivative. So this is just another way of saying that f is differentiable, which means that f is continuous, because one of our theorems is that a differentiable function is always continuous. So f is differentiable, f is continuous, but we're saying something stronger here, guys, that even f prime is still continuous. Okay, so the derivative of f is continuous. Okay, so then if there exists distinct points, and these are going to be w, x, y, and z, such that f of w is equal to f of x, and f of y is equal to y, and f of z is equal to z. Prove, now we're ready to get to the proof. We're going to prove that if all of that is true, that there exists a real number u with f prime of u equal to 1/2. Okay. Quite a bit of assumptions there, but I'm trying to come up with problems. As you can kind of see, they're using multiple ideas. We have a lot to cover here. So if I can make questions where we kind of touch on multiple things at once, then that, you know, kills 2 birds with 1 stone or whatever. You can get a little more mileage out of it. So this is another example that's like that. This is going to use multiple big ideas. Okay, so I would like the derivative of f at some point u to equal 1/2. What we know about the derivative is that it's a continuous function. So we're assuming that the derivative of f is not just existing, it's actually continuous. Okay. I'm wondering if anybody has any thoughts on what we could maybe play with here. So remember that f is differentiable. I've got these 4 distinct points. Okay, I don't really know where they are. I don't even know what order they're in, actually. So w might be there, x could be there, z could be there, and y could be there, for all we know. We really don't know what order they're in, but there's 4 distinct points there somewhere. And these points are given to me. So it's not just that they exist in some abstract sense. These points are actually given to me and they form some kind of, like, you can make a closed interval out of them. Giving too much away. It's a continuous function and I'm talking about closed interval, right? And actually it's more than continuous, it's differentiable. Is there any tools we have when we have a We have a derivative available to us. We can make closed intervals out of anything we want. Yeah, we could think about the mean value theorem. That's probably what I would be thinking about. The fact that the mean value theorem requires us to have a differentiable function on a closed interval. And so we're gonna have to talk in a minute about what closed interval we might wanna use. But, you know, then we can just see where that gets us. Maybe it's not gonna work. I don't know, but it's something to try. It's something to try. Let's see if we can try this. So for the solution, what kind of closed interval would you maybe want to apply the mean value theorem to? Based on what's given to you here, would there be a choice that might make the most sense?
Hey, you want to know? 0, 1.
You're thinking about it in terms of this, that the 1/2 is an output. The mean value theorem is gonna be an interval that's created on the x-axis. X to W? Yeah, why not? Because we already know that f of W equals f of x, let's just try it. Now, I don't know whether the interval goes from x to W or whether it goes from W to x. So we'll just write our explanation to kind of handle both scenarios. So let's just say we will apply the mean value theorem to f on the interval. Now, this is going to be the interval from W to X or X to W. Okay, we don't know which of those numbers is larger, but we'll just handle both cases at once. And what does it tell us? It tells us that there exists a U1 in the interval from W to X or the interval from X to W. Again, we don't know which one. Whoops. We don't know which one is the right one. So there exists a U1 within that interval such that f prime of U1 is equal to, what is it? F of x minus f of W divided by x minus W. Now, if the interval was actually the other way around, you would be putting these in the opposite positions and these in the opposite positions. It would be the same either way. So it actually doesn't matter whether, you don't have to like do two proofs. Like you can just kind of write this fraction once and it will be correct. What is this going to be equal to? Yeah, we assume that f of W is equal to f of x. And if that's the case, then this is equal to 0. So f prime of U1 is equal to 0. Okay, so we found a point where the derivative is equal to 0. And now, what else do we need to work with?
Do it again, but with Z and Y.
How about the y and the z part of it? And again, I don't know which one is on the left and which one is on the right. But let's rinse and repeat, guys. Let's also use the mean value theorem on the interval from y to z. So similarly, applying the mean value theorem to f on the interval from y to z, or it could be z to y, we don't really know, shouldn't matter, right? There exists, I'm gonna call it a U2. And this will be in the interval. Or the reversed interval, whichever one is the correct way of phrasing it. Such that f prime of U2 is equal to, so I'll write it as f of z minus f of y all over z minus y. We'll set it up like that. And what is that gonna give me? 1. Oh, interesting. Okay. So that gives me a 1. So we have one place where the derivative was equal to 0. We have another place where the derivative was equal to 1. And obviously they're not the same. So U1 cannot be equal to U2 because their derivatives were not the same. And I would like to find a place where the derivative is equal to 1/2. So now what am I gonna do?
Apply it to U1, U2. Mean value theorem from U1 to U2.
We could try to apply the mean value theorem to U1 and U2. So what would that do? I'm gonna just scribble that down for a second, so I could make another interval. I like this idea, and again, we don't know. We don't know which one is bigger, but we could think about this interval. What would happen would be there would exist, well, what we're hoping is it would be the U. In that interval such that. Now, you're applying the mean value theorem to F prime,
Yeah.
then that would give me this. F double prime of U is equal to F prime of U2 minus F prime of U1 all over U2 minus U1. And that would be 1 minus 0, and this is what we're ending up with. So we don't have a 1/2 over here, and we don't have the right derivative over here.
Value.
Okay, maybe this is not what we wanted. Guys, I don't mind chasing some of these ideas because this is the way it goes, right? I mean, it might happen to you on the exam, you're like, oh, I just did the mean value theorem twice, maybe I should do it again. Now, if the question had said something about the second derivative, I would definitely be thinking about using the mean value theorem on F prime to say something about the second derivative, but this problem actually doesn't involve the second derivative. So instead of the mean value theorem, I'm gonna erase all of this. Instead of that, we need to think more about the intermediate value theorem. Because we have F prime of U1 equals 0. And F prime of U2 is equal to 1, and F prime is continuous. Right? So let's add that to the notes now. So since F prime is continuous on the interval from U1 to U2, and again, I'm gonna add the possibility that it could be from U2 to U1, we don't really know which one is bigger or smaller. We apply the intermediate value theorem to, so remember that the way the intermediate value theorem is framed is you start with a fixed k value. And in this case, we actually want it to be 1/2. The k value is the output value. Okay, so this was given 1/2, so I put k to be 1/2, and so what does the theorem say? The theorem says there exists a u in that interval from U2 to U1 or U1 to U2. Now, the fact of the matter is it could be an open interval, it will be within the open interval here. It's not gonna be at the endpoints because F prime of the endpoints does not equal 1/2. But anyway, there exists a u with F prime of U equal to that value of k, which is 1/2. So that's how you do it. So the names are almost the same, intermediate value theorem and mean value theorem, right? The IVT versus the MVT, but then in fact, the point of the fact is, a lot of times, they're not used together. The intermediate value theorem never uses a derivative. It's just the original function. The mean value theorem is talking about the derivative. So it's rare to see a problem where both theorems come in use at the same time, but this is a good example of it, where that does happen. So anyway, it's kind of a nice problem. Again, something like this, I would be tempted to give a hint to kind of get you started on this, because there's quite a bit to it to kind of lift your way up to the final answer. Okay, we have done almost everything on my sheet, and I've got maybe time to do one more, do you think? Does that sound good? And then we'll give everybody a mental break. Let's do one that's not too crazy here, just to wrap this up. So I'm gonna do number 8. And then on Monday's review, I will just pick up where I'm leaving off now and give you even more practice. But let's do this. Let's define f from the closed interval from 0 to 8 going to the real numbers. I'm gonna give you a function here via. And now here is the function. F of x is a piecewise function and there's going to be 4 pieces, so give yourself plenty of room. It's going to equal 7 if x is equal to 0. And then it's gonna equal x squared plus 1. If x is strictly greater than 0 but less than or equal to 2. And then it is going to equal 7 minus x. If 2 is strictly less than x, which is strictly less than 5. And then I'm gonna use e to the negative x. If x is between 5 and 8 inclusive. So there is the function. And I'm gonna ask you a question about this function. I'm gonna ask you 4 questions about this function. Is f, part A, is it continuous?
Question.
Is it continuous on the closed interval 0 to 8? Part B is gonna be the same question for uniformly continuous. On the same interval from 0 to 8. Part C is going to be differentiable on that same interval. And part D is going to be Riemann integrable. On that same interval again, so 4-part question here. I just remembered something. What I wanted to tell you guys is that group work that we did on Thursday. Where you're seeing the relationship between continuous, differentiable, monotone, Riemann integrable, bounded. It's really pretty nice to know that, right? And we can add uniformly continuous into that discussion as well, because sometimes that's also a different idea. I realized, the thing I just realized is that I forgot to put the group work into Canvas. I've been so busy, so I'm gonna try to remember for 5 more minutes till after the review to go do that, in case anybody needs to. I think everybody in class on Thursday did finish it. Litsy's got this beautiful picture of it, the Venn diagram showing the relationships, because guys, you do not want to have to from scratch do all 4 of these parts. It's gonna take too long. The idea here is that these are related to each other. So if the function is differentiable, then for sure it's already continuous, right? And if it's uniformly continuous, it's already continuous. If it's continuous, then it is Riemann integrable, right? So using those relationships makes this a lot less daunting. Okay, so what would you maybe think to do first with this? I would too. I would probably try to draw a graph. It doesn't have to be a perfect picture. But you know, the thing is, guys, you have intuition about these concepts. You're allowed to use your intuition to figure these things out. You don't have to pretend that since it's Math 350, you have to figure it out from a technical point of view first. You can first just get the intuition right. So if I go from 0 to 8, make my domain, and f of 0 is 7. I'm gonna plot 7 right there. And then x squared plus 1 is a parabola shifted up 1 unit, right? But we have to put a circle on the left side, and then I start drawing my parabola like this, and it's filled in on the right side, and that gets me to x equals 2. And by the way, f of 2 is equal to 5. So I never promised that this was perfectly to scale, but I'm gonna do my best. So that's 5, and now. Oh, when I go to the next part of the domain from 2 to 5, let's see, 7 minus x is equal to 5, and then it drops down towards 2, right? Something like that, roughly. Again, doesn't have to be perfect. Doesn't have to be perfect. Oops, this should be an open circle on this end. Open circle on 5. And then, oh gosh, e to the -5, that's a very small number. That's gonna be way down here somewhere. And then, as x increases, that only gets smaller, so it's gonna drop off like that, something like that. So this is not drawn to scale at all, but I think it's gonna accomplish what we need for trying to figure out this question. So like, what is your, does anybody have already an intuition about the answers to all 4 parts?
I think it might be Riemann integrable, cause it's just discontinuous at a certain number, a finite number.
There's only a finite number of places where the graph has displaced points. You can, remember, to be Riemann integrable on 0 to 8, it's good enough for it to be Riemann integrable from 0 to 2, and 2 to 5, and 5 to 8. And on each of those intervals, I'm feeling pretty good about it. Cause maybe we could just explain that really quick here. So f is Riemann integrable from 0 to 8, since f is Riemann integrable from 0 to 2, and f is Riemann integrable from 2 to 5, and f is Riemann integrable from 5 to 8. Let's give reasons for each of these 3 smaller intervals here. In the case of the first subinterval, the function is actually, well, it's monotone or continuous, use either one you want. Remember, continuous functions are always,
Is it not
Riemann
monotone
integrable?
'cause 7?
I'm sorry?
Is it not monotone because 7?
There's one bad point,
Oh, okay.
so we're gonna
You
move
see
that
that,
point,
okay.
yeah, and so essentially, if we ignored that point.
Yeah.
This would be either, well, it's both monotone and continuous, you can use that justification. And all we've done is moved 1 point, okay, so I'll just say, up here, I'm just gonna say, since f is 1 point away from being continuous. I'll just put slash monotone, you can use either of those reasons, remember, both Riemann, both continuous functions and monotone functions are always Riemann integrable, okay? From 2 to 5, I think I'm going to just use the monotone reason. This is actually a monotone decreasing function. So f is monotone decreasing right here. And then from 5 to 8, we can do the same thing. So it's monotone decreasing basically from 2 to 8. We could have just, we didn't need to split the interval up at 5. As it turned out, we could have just gone all the way from 2 to 8 and it would have been monotone. That would have been a little less writing, but it's okay. And so putting it all together, it's Riemann integrable all the way from 0 to 8. So I agree with Litzy. I hope everybody else does too. Are people comfortable with that, with the justification of it and kind of how to think about it? You know, whenever you have these piecewise defined functions, you pretty much know you're gonna need to look at each piece, right, one by one and figure it out. Okay. What about these other questions? Continuous, uniformly continuous, differentiable?
Not differentiable.
No,
Sorry?
no,
No, no, and no, I think is what he said. He doesn't want any of these, well, actually, if this is a no. If this is a no, then so is this. By the way, on a closed interval, remember, on a closed interval, uniform continuity and continuity are the same. So if you say yes on one, you have to say yes on the other. If you say no on one, you have to say no on the other. So those would both be no, and if it's not continuous, then by the contrapositive of theorem 5.1, it's not differentiable. Really, you only need to explain A. You only need to explain A, so I'm just gonna, because B and C follow from that, so I'm just gonna make a little space here to give a quick reason. So F is not continuous. If I want it to be not continuous on the entire closed interval, I just need to find 1 point within that domain that it's not continuous. What point do you want me to focus on?
0.
0, okay, F is not continuous at 0. Let's justify that, so if we take the limit as x goes to 0 of f of x. That's simply the limit as x goes to 0, so if X is approaching 0 in some kind of a delta neighborhood. Remember, you can't go outside of the domain, so any delta neighborhood of 0 would only be one-sided. It would only be one-sided, you don't have a balance point on the other side. And so you are literally just taking the function as it's defined to the right of 0, which is x squared plus 1, and this is obviously equal to 1, and that's obviously not equal to f of 7. And so this is, what we're using here, guys, is that huge remark. We've talked about this a lot, used it a lot, and so I definitely think you should make sure you understand that and can justify continuity or lack of continuity at a point by using this huge remark. So the intuition is, I can't draw this graph without picking up my pencil. That's not gonna work on the justification for a Math 350 exam. You need to give me something a little more rigorous. This would be what I would be looking for. I mean, you also could do a epsilon delta proof and, choose epsilon equal to, 1/2 or something, and then, here's f of, so f of x minus f of c is way more than epsilon within that domain. So you could get your hands on the definition, it'd be a little more work, and that would be okay. But this is even faster, and I like that even better. So that's a no, and if it's a no on continuity, then it's no on uniform continuity and no on differentiable as well. So, yeah, this kind of question, well, I even had one like this on the third midterm, but now we even have this is 4 properties. all put together, all put together at the same time, so. All right, well, I have gone through most of the ones I had on this sheet. I got a couple left that I'll save for Monday, and then I'll probably add a few more for Monday as well, so that we have even more to practice. If you have any requests for topics, I'm gonna try on Monday to kind of cover everything again. But if there's certain things you think that we need to hit a little bit harder, I think one thing I would like to hit a little bit harder is the stuff on countable sets again, because I actually think that was hard even when they first did it. And now we've had this long layoff on it. So probably on Monday, you're going to hear me talking about countable and uncountable sets. I might do something with sequences where we actually use the definition. Today we did a monotone convergence theorem problem. But I'm going to try to cover all of the same ground, but maybe with some slightly different focus points on things that didn't get brought up quite so much here. That'll be my goal. But I think we did pretty good, actually. We didn't talk about everything. We didn't talk about Taylor's theorem. Yeah, we didn't talk a lot about countable and uncountable sets. There'll be a few things. I'll come up with some things to throw at you. Okay? Everybody out there in Zoom land, okay?
Yeah, I'm doing well.
All right, I might stop this recording and call it good for this session and let you guys go back to working on your proofs again a little bit. Does that sound fair?
Nice. Yep, of course.
I appreciate you coming though, and thank you guys also for coming. It's always nice to have people to listen. And I will be starting my office hours tonight